NEC Section 527.6, titled Ground Fault Protection for Personnel, clearly states that personnel must be protected against ground fault hazards as outlined within the section. This protection is achieved through various methods, one of which is the use of ground fault circuit interrupters, commonly known as GFCIs. The NEC specifically mandates GFCI protection for all 120-volt, single-phase, 15 and 20 ampere receptacles that are installed in specific locations. These locations include bathrooms, garages, outdoor areas, kitchens, laundry rooms, crawl spaces, unfinished basements, workshops, and other locations where a risk of electric shock exists. It's crucial to understand that tests, experiments, and developmental work are frequently carried out in many of these designated locations. Consequently, the requirement for GFCI protection extends to these activities as well. The assertion that similar activities somehow excludes tests, experiments, and developmental work is a misinterpretation of the code. The phrase similar activities refers to activities that share characteristics with those explicitly listed, such as being performed in environments prone to electrical hazards. The NEC doesn't provide an exhaustive list of every conceivable activity, but it sets a clear standard for locations and voltage/amperage combinations where GFCI protection is essential. To interpret the code correctly, one must focus on the intended outcome, which is to protect personnel from ground fault hazards. Tests, experiments, and developmental work often involve the use of electrical equipment in environments where the risk of ground faults is elevated. Therefore, these activities fall squarely within the scope of Section 527.6. Considering a scenario where electrical testing is done in a workshop, the workshop is explicitly listed as a location requiring GFCI protection for 120-volt, single-phase, 15 and 20 ampere receptacles. If a test involves using a piece of equipment plugged into one of these receptacles, GFCI protection is required. Without GFCI protection, a ground fault could result in electrical shock or electrocution. The same principle applies to experiments conducted in laboratories or developmental work performed in outdoor areas. Any location that falls under the NEC list of areas requiring GFCI protection also requires it for tests, experiments, and developmental work conducted within that area using the specified voltage and amperage. Furthermore, the NEC doesn't distinguish between normal activities and experimental activities. The focus is on the location, the voltage, and the potential for ground faults. An environment deemed hazardous enough to require GFCI protection under normal circumstances remains hazardous regardless of the specific activity being performed. To reiterate, the interpretation of Section 527.6 should be that GFCI protection is mandatory for tests, experiments, and developmental work when those activities are conducted in locations where GFCI protection is already required by the code for 120-volt, single-phase, 15 and 20 ampere receptacles. This interpretation aligns with the code's primary objective of safeguarding personnel from ground fault hazards. The misunderstanding that tests, experiments, and developmental work are somehow exempt from GFCI requirements likely stems from a narrow reading of the phrase similar activities. This phrase is not meant to create exceptions, but rather to ensure that the code's intent is applied broadly to cover a range of activities that present a similar risk of electrical shock. The NEC is a comprehensive document, and its various sections are intended to work together to achieve a high level of electrical safety. When interpreting any particular section, it's important to consider the overall context and the underlying principles. In the case of Section 527.6, the primary principle is the protection of personnel from ground fault hazards. This principle should guide the interpretation of all the section's provisions. To clarify, the NEC specifies requirements for ground fault circuit interrupter protection in numerous locations. Firstly, bathrooms require GFCI protection for all 120-volt, single-phase, 15 and 20 ampere receptacles. Secondly, garages also necessitate GFCI protection for the same type of receptacles. Thirdly, outdoor areas demand GFCI protection to mitigate the risk of electric shock in wet or damp environments. Fourthly, kitchens, particularly near sinks and countertops, require GFCI protection for 120-volt, single-phase, 15 and 20 ampere receptacles. Fifthly, laundry rooms, due to the presence of water and appliances, are mandated to have GFCI protection for the specified receptacles. Sixthly, crawl spaces, often damp and confined, need GFCI protection to ensure safety during maintenance or inspection. Seventhly, unfinished basements prone to moisture also fall under the GFCI protection requirement for the specified receptacles. Eighthly, workshops, where electrical tools are frequently used, require GFCI protection to prevent electrical accidents. Ninthly, other locations where there is a risk of electric shock, as determined by the authority having jurisdiction, also need GFCI protection. This list is not exhaustive, but it provides a clear indication of the types of environments where GFCI protection is deemed necessary to protect personnel from ground fault hazards. Tests, experiments, and developmental work often take place in these very environments, further emphasizing the importance of GFCI protection in these contexts. Let's consider some examples of how GFCI protection works in practice. Imagine an electrician using a power drill in a workshop. The drill is plugged into a 120-volt, single-phase, 15 ampere receptacle protected by a GFCI. If the drill's internal wiring develops a fault, causing current to leak to the metal casing, the GFCI will quickly detect this imbalance and trip the circuit, cutting off power to the drill and preventing the electrician from receiving an electric shock. Another scenario involves a researcher conducting an experiment in a laboratory. The experiment involves using a piece of equipment that is plugged into a 120-volt, single-phase, 20 ampere receptacle protected by a GFCI. If the equipment malfunctions and causes a ground fault, the GFCI will immediately trip, preventing any potential harm to the researcher. Similarly, a technician working on a prototype device in an outdoor area. The device is connected to a 120-volt, single-phase, 15 ampere receptacle protected by a GFCI. If a sudden rain shower causes water to enter the device, creating a ground fault, the GFCI will quickly disconnect the power supply, safeguarding the technician from electrical shock. These examples illustrate the critical role that GFCIs play in protecting personnel from ground fault hazards in a variety of situations, including tests, experiments, and developmental work. The NEC requirement for GFCI protection in specific locations is based on a thorough understanding of the potential risks associated with electrical equipment and the environments in which it is used. By adhering to these requirements, electrical professionals can significantly reduce the likelihood of electrical accidents and ensure the safety of themselves and others. It is important to note that GFCIs are not a substitute for other safety precautions. They are an additional layer of protection that complements safe work practices and proper equipment maintenance. Electrical professionals should always follow established safety procedures, such as wearing appropriate personal protective equipment, using insulated tools, and inspecting equipment for damage before use. Moreover, regular testing of GFCIs is essential to ensure that they are functioning properly. GFCIs should be tested monthly by pressing the test button and verifying that the device trips. If a GFCI fails to trip when tested, it should be replaced immediately. In conclusion, NEC Section 527.6 requires GFCI protection for 120-volt single-phase, 15 and 20 ampere receptacles in various locations, including bathrooms, garages, outdoor areas, kitchens, laundry rooms, crawl spaces, unfinished basements, workshops, and other areas where there is a risk of electric shock. This requirement applies to all activities conducted in these locations, including tests, experiments, and developmental work. The phrase similar activities does not exclude these activities from GFCI protection. The primary purpose of Section 527.6 is to protect personnel from ground fault hazards, and this purpose is best served by requiring GFCI protection in all situations where there is a potential risk of electric shock. By understanding and adhering to these requirements, electrical professionals can create safer working environments and prevent electrical accidents. The NEC also provides guidance on the installation and use of GFCIs, including requirements for wiring, grounding, and testing. It is crucial for electrical professionals to be familiar with these requirements and to follow them carefully to ensure that GFCIs are installed and functioning correctly. Ignoring the GFCI requirements not only poses a safety risk but can also result in code violations and potential legal liabilities. Authorities having jurisdiction, such as local building inspectors, are responsible for enforcing the NEC and ensuring that electrical installations meet the required safety standards. These authorities have the power to issue fines, require corrective actions, and even shut down operations if electrical hazards are found. Therefore, it is essential to take the NEC GFCI requirements seriously and to comply with them fully. Electrical safety is a shared responsibility, and everyone involved in the design, installation, and maintenance of electrical systems has a role to play in preventing electrical accidents. By working together and following established safety practices, we can create a safer environment for ourselves and others. In addition to the specific requirements of Section 527.6, the NEC contains many other provisions related to electrical safety. These provisions cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important for electrical professionals to have a thorough understanding of all these provisions and to apply them correctly in their work. Continuing education is also essential for electrical professionals to stay up to date with the latest changes in the NEC and to learn about new technologies and safety practices. The electrical industry is constantly evolving, and it is crucial to keep pace with these changes to maintain a high level of competence and safety. Many organizations offer training courses and certifications for electrical professionals, and these can be valuable resources for enhancing knowledge and skills. Furthermore, participating in industry conferences and trade shows can provide opportunities to network with other professionals and learn about the latest trends and developments. By investing in their professional development, electrical professionals can improve their career prospects and contribute to a safer and more efficient electrical industry. Remember, electrical work is inherently dangerous, and it is essential to take all necessary precautions to prevent accidents. By following the NEC requirements, using safe work practices, and staying up to date with the latest knowledge and skills, electrical professionals can minimize the risks and ensure the safety of themselves and others. The interpretation of electrical codes requires careful consideration and a thorough understanding of the underlying principles. If there is any doubt about the correct interpretation of a code provision, it is always best to consult with a qualified electrical inspector or engineer. These professionals have the expertise to provide guidance and ensure that electrical installations meet the required safety standards. The NEC is not intended to be a set of rigid rules, but rather a framework for ensuring electrical safety. It is important to apply the code with common sense and to consider the specific circumstances of each situation. In some cases, it may be necessary to exceed the minimum requirements of the code to provide an adequate level of safety. For example, in a particularly hazardous environment, it may be advisable to use additional GFCI protection or to install equipment with a higher level of protection. The ultimate goal of electrical safety is to protect people and property from harm. By keeping this goal in mind and by applying the NEC with diligence and expertise, electrical professionals can make a significant contribution to achieving a safer and more reliable electrical infrastructure.